Hi everyone, now let's talk about gravitational fields as part of topic D.1. So the essential question in this video is how do we model effects in gravitational fields? The first mini question is, what is a gravitational field? Well, it's a region around a mass in which another mass would experience a gravitational force. So if you imagine something very large like a planet, like planet Earth, then the gravitational field is going to surround the planet and it's going to be directed in toward the center of the planet. And that's not surprising because you can imagine something falling toward the center of the planet. So I'm going to indicate this with some field lines directing toward the planet. And what you'll notice about the field lines is if we extend some of these, as you get further and further away from the planet, those field lines get further and further apart, indicating that the gravitational field strength would be weaker as you get further from the object, and then as you get closer, you can see these lines get closer and closer together, indicating that the field strength gets stronger as you get closer, which is intuitive, goes without saying. If you imagine something much smaller, let's say this is our classroom, and this block represents the floor of the classroom. So here you can imagine the gravitational field lines, they wouldn't be radiating out like if you were looking at something large like a planet. They're going to be directed straight down. So you can imagine the gravitational field in our classroom just directed down, and there's really no measurable or appreciable difference between, saying, being close to the floor down here or being close to the ceiling up here. So the gravitational field strength would generally be the same when you're talking those short kind of distances. Oh, in case you weren't able to pick up on this, this top would be the ceiling, assuming I'm spelling ceiling correctly. So the gravitational field pointing down. Okay. So what is gravitational field strength? Well, it's the force per unit mass that would be experienced by a small test mass placed at that point. We're already familiar with the variable. It's g. And g is equal to the force divided by the unit mass. So essentially, how much force 1 kilogram of mass would experience at that point in the gravitational field. The SI unit is newtons per kilogram. Now we're on the surface of the Earth. We're used to seeing g as 9.1 meters per second squared because we refer to it as the acceleration of gravity, or 9.81. Here this would be 9.81 or 9.8 newtons per kilogram, and a newton per kilogram is the same thing as essentially if you shake out the units, it's the same thing as a meter per second squared. So we recognize this as 9.8 or 9.81 depending on what source we're looking at. So to find the gravitational field strength around a large mass, such as a planet, we're going to combine these two expressions. So we know g is equal to the force of gravity experienced by an object divided by its mass. And from the previous lesson, we know that the force of gravity is equal to the universal gravitation constant, g, times m1 times m2, so the masses of the two objects divided by the distance squared. Well, if we combine these two expressions, if we say, okay, we're going to take the force of gravity and we're going to divide it by whatever the mass is of the smaller mass, right? And often within this expression up here, m1 is a smaller mass and m2 is the larger mass, like the planet. So if we take m and we divide it by the smaller mass, m1, then we're going to get g times m1 times m2 all over r squared, but then that's going to be divided by m1 because we divided both sides by m1. So this is going to simplify into g times m2, which would be the mass of the larger object, usually the planet, divided by r squared. And often the mass for the larger object, we give that a capital M. So gm over r squared. R squared, which is equal to F over m, which we know is equal to g. So we've got this new expression. We can say g, or the gravitational field strength, is equal to the universal gravitation constant times the mass of the planet divided by r squared. Okay, you'll notice that the gravitational field strength around the planet follows an inverse square law. It's divided by r squared. So that means if you get twice as far away from an object, then your gravitational field strength decreases to 1/4. If you get 3 times away, it decreases to 1/9. So it follows inverse square law. Okay, what if a mass is in multiple gravitational fields? So if we have 2 or more masses and they're both creating gravitational fields at a certain point, then the total field strength is determined by adding the individual fields, since they are vector quantities. So let's say we've got a planet and we've got a moon. We know the planet has a gravitational field, which we can represent by these field lines. And the moon has a gravitational field, which we can represent by these field lines. And you can see that a point like this little dot here, maybe that represents a spaceship, is going to be affected by both gravitational fields. So they're going to behave like they're going to be vector quantities, right? We can figure out whatever the strength this one is, we'll call that G1. Whatever strength this one is, G2, and the actual amount of gravitational field strength acting on an object is going to be the difference between these two, since they're acting in opposite directions. We'll do a practice problem that involves that here in just a second. You can also imagine that there's a point at which these will cancel out, right? That the gravitational field strength heading in one direction will equal the gravitational field strength heading in another direction. And so for a split second, if let's assume this is a spaceship moving from the Earth to the moon there, that it has a point at which it has a net zero gravitational field strength. Okay, with all that in mind, let's try some practice problems, and this will make a little more sense. So worked example D1.4, this is on page 420. A student measures the time it takes for a stone to fall from rest to the ground from a height of 1.18 meters to be 0.49 seconds. Determine the value this gives for the acceleration due to gravity at her location. Okay, so this is a review of some kinematics, some kinematic equations. So let's identify what we know. We're going to fall from rest, so u equals 0, to the ground from a height of 1.18 meters. So we'll say s is equal to 1.18. That's going to be our displacement, 1.18 meters. And the time is equal to 0.49 seconds. Determine this value gives for the acceleration due to gravity. So acceleration is our question. That's what we don't know. So we let's see, fall from rest to the ground at a height of okay. So we need to determine the acceleration. We need an equation that relates these characteristics of motion. Let's see, I think we have S is equal to ut plus 1/2 at squared. That's one of our kinematic equations. This works for this situation. We'll switch to blue as we solve it. This first term, since u is equal to 0, this first term goes to 0. So we can say that S is equal to 1/2 at squared. And we know t, we're trying to find a. So if we rearrange this for a, we get acceleration is equal to 2s divided by time squared. Okay, so let's plug in our values. Acceleration is equal to 2 times s, which is in SI units, 1.18 meters, divided by time, which is 0.49 seconds, and that needs to be squared. The units work out because we should end up in meters per second squared, so those units are okay. So take a second to plug this in your calculator. Do that while I'm doing the same, please. So let's see, we've got 2 times 1.18. All that is divided by 0.49 squared. And we get 9.8. Keeping, let's see, 2 significant figures, we have 9.8 meters per second squared, which we know that to be the acceleration of gravity near the surface of the Earth. So this one checks out. So this was actually a kinematics problem, a little bit more than a gravity problem, but it had us practice or review this concept of gravity as well. Worked example D1.5, page 120. Determine the gravitational field strength on the surface of a planet which has a mass of 4.87 times 10 to the 24 kilograms and a radius of 6.05 times 10 to the 6 meters. Okay, so we're going to use, what we want is gravitational field strength. So we're looking for, our unknown is g. We know the mass of the planet. We're going to represent that with a capital M. Mass of the planet is 4.87 times 10 to the 24 kilograms. And we have a radius of 6.05 times 10 to the 6 meters, and 10 to the 6. And we know we're on the surface of the planet, so we're only one radius away then from the center of the planet, which is where the gravity is really acting. So we can use this expression. I'll switch to blue here. G is equal to the universal gravitation constant, G times m over r squared. We can plug in some values. The book answer is 8.87 newtons per kilogram. So let's see if we get that answer. 8.87 newtons per kilogram. Okay, so we're going to get G. Hopefully by now you're starting to memorize this. It's 6.67 times 10 to the minus 11 newtons, newtons meter squared per kilogram squared, times the mass of the planet, which is 4.87 times 10 to the 24 kilograms, divided by the radius. Now, like we said, we're on the surface of the planet, so we're only one radius away from the center. So we'll say that the radius is 6.05 times 10 to the 6 meters, and that needs to be squared. So our meter squared here is going to cancel out with those meters squared, and this kilogram is going to cancel out with one of these kilograms. So we'll get a kilogram minus 1. So our unit should be newtons per kilogram, which is what we want since we're looking for the gravitational field strength. So take a second to put this in your calculator while I'm doing the same. All right, 6.67 times 10 to the minus 11 times 4.87 times 10 to the 24, 4.87 times 10 to the 24 over 6.05 times 10 to the 6, and that's squared. I'm getting an error. Okay, finally, I get 8.87 newtons per kilogram. 8.87 newtons per kilogram. And that, according to our book, is the planet Venus. Okay. Moving on, predict a value for the gravitational field strength on the surface of Saturn, which has a radius of 5.8 times 10 to the 7 meters. Now this one, here we're given a different piece of information, just in case we see one of these. We're told in the book example that the density of Saturn, which is rho, is 687 kilograms per meter cubed. So 687 kilograms per meter cubed. Okay, so we want the gravitational field strength. So we're going to use this expression. G is equal to, our gravitational field strength is equal to the universal gravitational constant times the mass divided by the radius squared. Gravitational field constant, we know mass is going to be density times volume, still over r squared. Volume of a sphere is 4/3 pi r cubed all over r squared. Well, the r squared is going to cancel out with part of that r cubed, so this is going to equal g times rho times 4/3 pi r. Okay, well, this isn't too bad. So this is going to be let me move this over, erase this a little bit. Erase. So this is going to equal 6.67 times 10 to the minus 11 newtons meter squared per kilogram squared times rho, which is, or the density, which is 687 kilograms. This is per meter cubed. Kilograms per cubic meter times 4/3 times pi times r, which is 5.8 times 10 to the 7 meters. Let's see if our units work out. So we should end up with, since we're calculating gravitational field strength, we should end up with newtons per kilogram. Let's see, this meter squared and this meter are going to cancel out with this per meter cubed. This kilogram is going to cancel out with one of those kilograms, and so what's left over is newtons per kilogram. Okay, that works out. Take a second to put this in your calculator while I do the same. So it's going to be 6.67 times 10 to the minus 11 times 687 times 4/3 times pi times 5.8 times 10 to the 7. And this equals approximately 11 newtons per kilogram. Okay. And if according to the accepted value is 10.4, so we're in the ballpark there. Okay, let's take a look at this one. Two parts here. In the figure below, which is not drawn to scale, point P is a point midway between the centers of the planets A and B. At P, the gravitational field strength due to A is 4.0 newtons per kilogram, and that due to B, this is at point P. No, wait a minute. At point at P, which is here, the gravitational field strength due to A is 4.0 newtons per kilogram, and that due to B is 3.0 newtons per kilogram. Determine the resultant gravitational field strength at P. Okay, so not too bad here. So at P, we're told that the gravitational field strength due to A, which is going this way, is 4.0 newtons per kilogram. And the gravitational field strength due to B, which is going this way, is 3.0 newtons per kilogram. So that means the resultant gravitational field strength would be the difference between these two. So it's going to be 4.0 newtons per kilogram minus 3.0 newtons per kilogram, which equals 1.0 newtons per kilogram, going in the direction of A. So we'll call this direction positive, this direction negative. Calculate the combined gravitational field strength at point Q. P and Q are the same distance from A. So now point Q, here's where we have to apply some logic. At point Q, just a minute, let's do that better. At point Q, then the gravitational field strength from B will be 1/9 as much as it is for point P. You'll notice that as I zoom in here, point Q is 3 times further away from planet B. So here's planet B, here's point Q. So point Q is 1, 2, 3 times further away from planet B than point P is. So that means the gravitational field strength for point Q must be equal to 1/9 of what it was from point P. Okay, so if point P had a gravitational field strength due to B of 3 newtons per kilogram, then it must be 1/9 of that. So it must be 3/9 or 1/3. So point Q from B should be 1/3 Newton per kilogram, or and we're going to say negative 0.33 newtons per kilogram. And we'll say negative because we're going to define this direction as being negative. Okay. Now point Q is the same distance from from planet A as point P was. So point Q should have the same gravitational field strength, just going in the other direction. So point Q, where point P's gravitational field strength due to A is 4.0 newtons, that should be the same for Q, but going in the other direction. So from A, so point Q's gravitational field strength from A is actually equal to negative 4.0 newtons per kilogram. So we should get something. Flip over to the page here. Negative. So point Q from both A and B should be the combined effects of those. So negative 4.3 or 4.33 newtons per kilogram. Okay, take a look at that one. Looked at the worked example on page 422. Let me know if you have any questions about that one, because that was a little bit weird. And that's it for this video. So let me know if you have any questions, and I'll talk to you soon. Bye, guys.